Welcome back to the AJR Podcast Series on Diagnostic Excellence and Error. I'm your host, Francis Deng, a radiologist at Johns Hopkins. Today, we're tackling the intersection of diagnostic error and technology. How can radiologists use AI for quality assurance and prevent major diagnostic errors? My guest today is Dr. Benjamin Strong, a board-certified radiologist and the chief medical officer at Virtual Radiologic. Dr. Strong started in internal medicine, actually, and worked for a number of years as an emergency physician before returning to training as a radiologist. And he's been at vRad now for 20 years. vRad is one of the nation's largest teleradiology practices with 533 physicians operating in all 50 states, reading 6.5 million studies a year. He's taken a deep dive into their quality assurance and malpractice records over many years and shares some of these insights through a free online CME course provided by vRad, as well as at conferences like the RSNA, where I heard him this past year and thought he would be a terrific guest for this podcast. So welcome, Ben.
Thank you, Francis. Pleasure to be here.
Ben, you've done a deep analysis of the closed malpractice claims against vRad radiologists over the years, as well as your own internal peer review QA data. Can you give us some top-level highlights of what you've been able to find?
I guess top level, my biggest concern has been identifying the pathologies that are most frequently missed through our QA data, or those that are most expensive from a med mal standpoint. Of course, expense is often tied in medical malpractice to patient outcomes. So that obviously means most frequently linked to poor patient outcomes as well. And from that data, we developed a list we call the Big Five. So there are 3 pathologies most frequently linked to medical malpractice indemnities, and those are aortic dissection, spinal epidural abscess, and superior mesenteric artery occlusion. And then from a QA perspective, the most commonly missed entities are intracranial hemorrhage and pulmonary embolism. So that's what we're very proud of at vRad, that we had the data to derive those conclusions and then use that information to feed back into our processes. So we use the examples that we've found through medical malpractice or through quality assurance programs, and we use that to generate our internal educational programs. And we've also used that information to direct our development of artificial intelligence algorithms.
That's very interesting. So your citation of the Big Five reminds me of a similar concept in a previous episode with Dr. David Newman-Toker, which was the Big Three, which is serious misdiagnosis-related harms in malpractice claims, which he cited were vascular events, infections, and cancers. I noticed missing from your list of the top 5 were the cancers. So what happened to the cancers in your QA and malpractice data?
I think the main thing is that vRad is primarily an emergency teleradiology practice. And so we don't see as much cancer as a typical practice would on a percentage basis. And I think that's a significant contributor to the lower ranking of cancer misses in our data set. Certainly, they still were present, but not anywhere near the impressive prominence that the pathologies I just cited had.
And that difference in setting, I think, is important for talking about the malpractice risk or error risk inherent, because emergency radiology is probably at a higher risk for major diagnostic errors, right? These patients are undifferentiated and they're coming in with poor clinical history provided to the radiologist, and you're trying to suss out a lot of different diagnoses in a given patient.
And I would add to your list of contributory factors the fact that oftentimes these are presentations of life-threatening illnesses. So you really have one shot at making the right diagnosis, and then may, as a result of a missed diagnosis, have a terrible patient outcome rather quickly before there's the opportunity to potentially correct that. There's no question that emergency medicine carries a much greater risk.
In terms of the error rate that you found in your QA data, how does that compare to what's been cited in the literature?
We do know our error rate, and we have tracked it for more than 20 years, stands at about 1.3 misses per 1,000 studies, which is significantly lower than the main published data that's out there. Typically, I see the SOPA study, the Wilson-Wong study, and the Wu meta-analysis I would say, are probably over the last 20 years, the three most often cited quality assurance publications.
Here are the major findings from those studies. David Safa and colleagues published in JACR in 2004 an analysis of their practice's 2% double reading QA data, which included about 3,800 general radiology cases. They found an overall disagreement rate of 30 per thousand, but did not separate major and minor disagreements. Wilson Wong and colleagues published in JACR in 2005 an analysis of discordant interpretations in teleradiology prelims out of nearly 125,000 cases. The major disagreement rate was 1.3 per thousand. Mark Wu and colleagues published in Radiology in 2013 a systematic review and meta-analysis of the discrepancies in CT interpretations, so excluding radiographs and other modalities. And this review included the aforementioned Wong study, where 3/4 of the teleradiology interpretations were CT. The pooled major discrepancy rate in this meta-analysis was 24 per thousand, although there was considerable heterogeneity in between studies.
And so at 1.3, our error rate is significantly lower than the other published data. But I will say that has held up for many years and has shown very little variation, just steady improvement is all. I attribute much of that to the fact that we have a very robust quality assurance program. Even today, with the decrease in preliminary imaging that we've seen, we still are overread on average at a rate of about 20% on a per radiologist basis. And I think that is a huge contributor. The other contributing factors are, again, that we use the quality assurance data to inform our educational programs, which we offer free both internally and externally at vRad. So I think that has done a lot to reduce our error rate over the years. Certainly, when I look at our data, I know that is our real rate. I would add, though, that we may have differences in what we classify as a major miss and a minor miss. And so I wonder if it could be some bookkeeping differences that contribute to that reduced error rate as well.
That makes a lot of sense. Differences in how you actually capture the errors may account for those differences in rates. But regardless, in a practice of your size at vRad, even if the rate is low because of the great volume of studies you're reading every year, there must be a significant number of major misses. And of those, a proportion do go on to become malpractice claims. And I wonder if you can speak to a little bit how the data on the malpractice and the QA data at vRad shaped the priorities for not only developing educational content, as you mentioned, but also developing in-house AI critical finding detector algorithms. Because there are some pathologies that you mentioned that didn't strike me as really the focus of a lot of commercial attention. Certainly we have pulmonary embolism detectors, intracranial hemorrhage detectors, but what about spinal epidural lesions or ischemic bowel? I don't hear about that quite as commonly.
Absolutely. We were able to identify, I think, a few hidden gems that clearly were contributors to large medical malpractice indemnities, but also numerically, just in absolute numbers, a common cause of indemnities. Again, we're really proud of the fact that we've actually used our data to identify the problems that we then sought to fix. And I would say that's significantly different than most practices that are trying to implement artificial intelligence. I have a joke, an analogy that I always call most of the practices that I see that are trying to implement artificial intelligence, they strike me as hungry shoppers. They go to the store with an appetite. They know that everyone is doing AI and they're out to get some AI as well. And they walk the aisles with their basket and they say, well, this looks good. And oh, that might be cute. I literally heard the head of AI at one large practice refer to a potential algorithm as cute. And I think that's the wrong way to go about it, right? They get home and they have a basket full of sardines and kale and gummy bears from which they cannot possibly make a hearty meal. And it all came from the fact that they didn't first identify the problem that they were out to solve. And so I think that's an important step that differentiates vRad, that we have the data, we evaluated the data, analyzed it, and came up with the problems that we then wanted to address. there's a lot of discussion about should you build or should you buy? And I think most people don't really have the option of building AI. They don't have the software engineering bench to do it. They don't have the robust image set data to actually create algorithms. But I think that just identifying the problem that you need to solve gets you a long way towards success with AI. And that's where things fall apart. You come home with a shopping basket full of algorithms for this or that, and you didn't really know what problems your practice had, given your patient demographics, your specific location, and the prevalence of pathologies in your region. It changes things significantly, I think, to identify the problem first.
Regardless of if your practice is going to buy or has the capacity to build, there are a lot of upfront costs to developing or getting these algorithms and implementing them, and also ongoing resources in terms of radiologist time in reviewing results and managing false positive hits on these algorithms. So when it comes to rare pathologies that are critical, nevertheless, like SMA occlusion or spinal epidural hematoma or abscess, how did you quantify the expected return on investment of these models or processes?
It becomes a numbers game once you get a hold of all this data. So we're able to look at exactly how many of each of these pathologies resulted in a medical malpractice case. And then using natural language processing, we can go through all of our archived reports, even those where there were no errors. And we can actually determine the incidence of all of these pathologies on a per relevant study basis. And with that information, you can actually calculate what we call the standard miss rate. You can see how frequently is that particular pathology missed when present. And that's by taking the ones that we know went to medical malpractice or became QAs and dividing that into the total incidence that we find through natural language processing. Once you've acquired the standard miss rate, you can also calculate what we call the medical malpractice conversion rate. You can show the percentage of misses in that particular pathology that will convert ultimately to a medical malpractice indemnity. And we're also able to calculate the average cost of a medical malpractice indemnity for each of these pathologies. With all of that data, the standard miss rate, the medical malpractice conversion rate, and the average indemnity for a medical malpractice case, you can very easily calculate the return on investment that you get out of development of these algorithms. And that's been particularly powerful in terms of making the case for the development costs, both from the financial side and the staffing side for the hiring of software engineers and the physician involvement. We use physicians both to annotate images to feed into our convoluted neural network. And we also use physicians to overread those cases that are flagged by AI. So it is expensive to do, but with the data that we have, we can point quite clearly to a total savings per year based on the number of AI algorithm catches on these specific pathologies that we have every year. And we actually apply it after the fact, so we know that they would otherwise have been missed.
Oh, really? Can you tell us more about that workflow?
We apply our AI algorithms to every relevant case coming in. We use the artificial intelligence algorithm to flag those cases where the AI says this pathology is present. We use that to expedite the study on the work list and get it read more quickly based on that output. But we don't share that output with the radiologist. So the radiologist then will read the study, issue a report, and we take natural language processing and apply it to that report and determine, does the report content match the output from our artificial intelligence algorithm? If they match, then everyone is happy. We do nothing further. But if they don't match and the AI says there is a miss here, then we send it to an additional radiologist who will adjudicate and decide whether there is in fact a miss. and communicate back to the original radiologist.
Gotcha. That's a very interesting workflow. So let me make sure I have that right. There's an AI that runs pre-radiologists to help triage things on the work list, but that is not displayed to the interpreting radiologist. And then the AI runs post-report to check the AI detector result against the radiologist report. And if there is a discrepancy, it's sent to a second radiologist for review. Presumably, this process allows you to track exactly the performance of both the AI and the radiologists, so you can have good data as to how both parties are performing.
Yes, absolutely. In using a system like that, we know then that those that are caught by AI were actually initially missed by the radiologist. And so we can point to the number of AI catches of those specific pathologies and compute an average indemnity by using the medical malpractice conversion rate and the average indemnity cost. And we can actually calculate the savings for a given year by using these algorithms. So that's how it all fits together.
The field of radiology AI is rapidly advancing with many different applications. In your experience with AI so far, has there been a type of AI that has made a particularly big impact on your clinical practice?
We've been doing this about 10 years. We built our first AI algorithm in 2015. And in the years immediately following, we built our natural language processing capability. So we built our own inference engine that powers our natural language processing. And in retrospect, I look back on them and think, natural language processing, which I consider a subset of artificial intelligence, natural language processing has probably made the bigger contribution to just the quality of care in our practice than even the image detection algorithms. NLP is useful for so many things, for the categorization of reports, for reporting prompts, for the inclusion of certain information. It helps in retrospective reviews, epidemiologic, or identifying the incidence of pathologies, or selecting, for that matter, the pathology examples from our archives that should be used to generate AI image detection algorithms. We can go back in our archives, find reference to the specific pathologies we're looking for, pull those image sets, and thus prime the CNN pump, essentially, to build algorithms. So it's been an incredible contributor and a big part of how we've gotten where we are, right? So I would encourage anyone setting out on this path to first lock down your natural language processing capabilities, because it's what will enable you to take that additional step of building image detection algorithms.
Your statement that NLP has made a bigger contribution has the implication that the image detectors are not perfect. So I'm wondering what you found with your in-house AI algorithms for image detection in terms of their performance to actually detect the findings.
Yeah, NLP has definitely been an enormous contributor along these lines. It allows for us to have ongoing evolution of our image detection algorithms. If you think about how I just described NLP being applied, it's been applied to all of our AI algorithms, checking their accuracy from the moment that we first create an AI algorithm. And the system that we use, honestly, it's an upshot of the fact that the FDA is very slow and very expensive in their approval of these sorts of AI algorithms. We actually have approval for the prioritization feature that I explained. Honestly, if you look out in the marketplace at AI algorithms that are being sold, the vast majority of them only have that level of FDA approval. If you actually are shown an output from an AI system, it will say right across the top in big red capital letters, not for diagnostic use. And it's interesting that our use of NLP, where we're applying it after the report is created, and thus checking the accuracy of the radiologist reporting, but also the accuracy of our algorithms, allows for a continuous cycle of development to go on behind the scenes, where we're constantly feeding the disparate outputs from NLP and AI back into the system. And we see, therefore, a gradual but continuous improvement in the performance of these algorithms. So because we know that the algorithms are not perfect, we are using that second radiologist check to make sure that we don't have over or under implementation from a clinical standpoint. And that system has served us very well. So when we start any of our artificial intelligence algorithms in production, they've generally been created by the process I described, where we identified reports and image sets that contain that pathology, create a basic algorithm, and then in ongoing fashion, we're using it to highlight and expedite cases before the radiologist sees them, but then we're also using it to determine the absolute truth after the report is created. So that continuous cycle allows our algorithms to evolve, which is a funny addition or a beneficial side effect of the fact that we don't actually seek FDA approval for our algorithms. Because if you get an FDA approval for an algorithm, you're then pretty much stuck with whatever performance that algorithm is currently delivering. They don't let you tweak it and constantly evolve in response to new data. And so we've been very fortunate. And again, it was just an unpredictable side effect of the initial implementation, how we first put this together. The performance of algorithms, therefore, is a moving target. When we first put algorithms out, they will be as low as 40% in sensitivity and usually probably in the 60% range for specificity. And very quickly, they improve significantly. And I would say those that we call mature algorithms, where we're using them all the time in the system that I described, our QA safety net system, we call it. Those algorithms typically are on the range of about 85% sensitive and over 95% specific. So that's the typical range of performance that we see. And again, each algorithm evolves at a slightly different pace, depending on how much feedback we're able to give the system, essentially. But that's where most of them have been ending up now, is in the mid to high 80s sensitivity and in the high 90s for specificity.
If the AI performance improves further, do you think there will be time savings that impact your bottom line?
I hear people talk all the time about, there's such a shortage of radiologists. And one of the things we're all really counting on is artificial intelligence stepping in and helping radiologists from a productivity standpoint, or just taking over some of the lower end reads. I don't actually see that happening anytime in the near future. I think we've found the sweet spot for AI application, and that is as an imaging safety net, where we're checking for specific pathologies that we've determined are missed frequently or that are so destructive when missed. And that's what we're really focusing on. I don't see a lot of contribution from an AI perspective to radiologist productivity. And I certainly think we're a long way from just replacing the radiologist with a robot in the chair. It's an interesting kind of additional point that has arisen in our work in this. We've noticed that providing a radiologist with a pre-prepared report, a pre-populated report, doesn't save time. In fact, in the vast majority of cases, it takes the radiologist longer because they have more information to assimilate, more kind of persnickety editing to do, and it ends up taking them longer than just preparing their own report. The other thing I'd mention is most of our algorithms are pretty specific to pathologies. And just taking one single element out of a radiologist's search pattern, saying, oh, you don't need to search for lung nodules anymore because we'll find those. It's probably a bad idea. For one thing, it only saves you perhaps a few seconds, and it causes more, I think, cognitive noise for the radiologist, right? To be altering the search pattern or stopping yourself and saying, oh, I don't need to look for this nodule. Right there, you ate up the few seconds that you're probably going to save by not looking for nodules. And so I really don't think that using AI in its current state is a productivity tool, and it certainly is not going to be the solution for the radiologist shortage, as I frequently hear touted.
I want to cite a specific example, especially because I'm a neuroradiologist, of the spinal epidural lesions. So a vRad group has published on this in the year 2023 in the journal Spine, Robert Harris and others, on their machine learning model for detecting what they call critical epidural lesions on CT images. So critical epidural meaning large epidural hematomas or abscesses that are longer than one vertebral body length and could be compressing the spinal cord. And they found that at that time, at least, so you said the performance is a moving target, but at that time, on prospective data, the model correctly prioritized 2/3 of 18 epidural lesions diagnosed on the initial read, but also found 17 missed epidural lesions over a 90-day time period in the teleradiology workflow when this model was implemented, suggesting that half of critical spinal epidural lesions visible on CT are being missed on initial diagnosis. And this rate actually seems plausible to me because usually the spinal canal is not an important part of the search pattern for a lot of radiologists. And these pathologies are so rare that we often forget about looking at that location, especially in a patient who doesn't otherwise have significant spine trauma. Do you have any commentary on this specific example?
You do bring up an interesting point, Francis, and that is that the awareness of our radiologists has risen significantly around these specific pathologies as a result of the work that we've done. I can't tell you how many people have come back to me and said, boy, I'm never missing one of those again now after seeing your presentation. And it's really increased the prominence of these specific things on people's search patterns. And I'd say that the two that suffer the most from an absence of search pattern were spinal epidural abscess and superior mesenteric artery occlusion. And yeah, those were the initial run at spinal epidural abscess. Fortunately, we have found that the standard miss rate for epidural abscess is lower than that. It is around 5%, though, which is still significant. And I attribute that current number probably to heightened awareness by our radiologists as well. The overall winner for standard miss rate from the big five pathologies this year was superior mesenteric artery occlusion, which came in at 18%. The aortic dissection was just under epidural at 4%. PE is between 2 and 3%, the standard miss rate. And the ICH miss rate is actually lower than 1%. It's about 0.4 or 0.5 for that standard miss rate. And so that's where they all fall out. And the superior mesenteric artery is the current winner, although spinal epidural abscess did win the year before that.
That's very interesting. I want to return to just a point about the financial bottom line. I heard that vRad self-insures, right? And so that kind of ties financial risk directly to your diagnostic accuracy. How does this structure motivate your organizational directives to adopt AI safety net QA programs?
I think it had a significant impact. Certainly, we track our medical malpractice expenditures more closely, I think, than a lot of practices. But we self-insure, but we also have a safety net of medical malpractice insurance from a third-party carrier. So in extreme events, we still do carry insurance. So we have a mixed hybrid approach. But even if you are fully insured by a third-party malpractice carrier, it still is worth doing this because in our pre-AI days, we were able to go to our carriers and show them the quality assurance data that we kept, the percentage of overreading that we accomplished, and again, our use of that information to feed back into educational programs. And it actually carried significant weight in terms of negotiating your rates for medical malpractice coverage. So it can be a significant contributor, whichever type of medical malpractice coverage you're actually carrying. But beyond that, then, Francis, I'll say it is a compelling argument to put up all the calculations in series to show where they were derived from and just point to a number at the end that says, we saved $8 million last year in medical malpractice indemnities. That makes everybody happy and shows a clear return on the investment.
I want to end with a final question, which is, what is your future outlook on the use of AI in improving radiologist performance and improving our quality in radiology?
That's a very interesting question, and my answer to it has changed dramatically over the last year. Obviously, we were pathology specific in our initial efforts to develop artificial intelligence. We were picking those pathologies that were salient, and we were building algorithms specifically to identify those. If you'd asked me a couple of years ago, I'd have said that's going to be a long road to develop specific algorithms for each and every pathology, right? And interestingly, too, I wasn't sure where we were going to go after really getting a handle on the big five. Because if you look at the standard miss rates, the medical malpractice conversion rates, it becomes quite difficult to find other pathologies that will warrant the effort. There is a real drop-off on the return on investment, right? Once you get outside those pathologies. So we were pivoting. We were saying we can probably focus our efforts more on operational assistance through AI. We can probably focus more on reporting content control with our NLP. So that's where we were a couple of years ago. Now, generative AI has just thrown a wrench in the works. Nobody is sure what's going to happen with this. Dr. Harris, Robert Harris, who you cited earlier, he is the head of our AI development team, and they have certainly pivoted. They're working almost exclusively with generative AI now. The possibilities are protean. There is a breadth to the pathologies that generative AI can address that is completely different compared to the pathology-specific algorithms we've been developing to date. So I really don't know where things are going to head. I think that the potential AI outputs are going to become far more comprehensive in the coming years, and I think it could really significantly speed up the timeline of AI development. Those are all predictions, though, based on probably less than a year of serious dedication to generative AI development. So we'll have to wait to see. Although I still say, oh, you're trying to replace radiologists. We're not there yet. AI as it exists today is not a threat to the existence of the radiologist. In fact, I see it as really making the lives of radiologists that much more satisfying, that they may be in a situation where they're using AI as an adjunct, offloading the drudgery of everyday radiology to some degree.
And not just offload drudgery, but also mitigating errors and enhancing patient outcomes. I want to thank you, Dr. Ben Strong, for sharing with us your invaluable insights on how AI and data-driven strategies like the Big Five are transforming diagnostic excellence in radiology today.
Thanks, Francis. Pleasure to be here.
And thank you to the listeners of the AJR Podcast Series on Diagnostic Excellence and Error.
I'll catch you next month.